Hi, I'm Tim, and I'll present our work titled Global Local Self-Distillation for Visual Representation Learning. The goal of self-supervised visual representation learning is to learn a general representation of an image suitable for downstream tasks by using a loss that does not depend on labeled data. Most previous works aim to learn a representation at the image level by training it to be invariant to standard data augmentations. However, images have inherent spatial structure which could be exploited to apply additional invariance constraints on the local representations. This leads us to a dual objective where on the one hand, coherence between global representation is enforced, and on the other hand, coherence between pairs of local representations is enforced. However, an exact correspondence mapping between the local representations in the two crops does not exist. Ideally, local representations should be matched based on semantics. This can be approximated in two ways. Previous work SVIT uses the similarity of local representations to approximate the correspondence mapping. However, we use a distance metric in the original input image grid to approximate this correspondence mapping and compare both approaches. In both cases, the high-level framework is the same. We take an input image X and apply data augmentations to obtain two different views, x tilde1 and x tilde2. These views are passed to two different encoders to obtain two global representations and two sets of local representations. All representations are passed to their respective heads. Given these projections, we can compute two losses, a global and a local loss. The sum of the two losses is minimized with regards to the weights of the students. The global loss is simply the cross-entropy between the projections of the two global representations. Instead of looking at equations for the local loss, let's visualize it. On the left side, we have the similarity matchings, and on the right side, we have the geometric matchings. In both cases, coherence between the local representations on each end of a colored assignment is enforced. On standard ImageNet downstream tasks, we observe similar performance for the two types of matchings and observe a performance improvement with regards to the vanilla baseline with a single global loss. To measure the robustness of the pre-training, we restrict the training dataset to subsets of ImageNet. We observed that geometric matchings always outperform the vanilla baseline irrespective of the dataset size, and that similarity matchings are very hurtful in low data regimes. We corroborate our findings by training on smaller scale datasets and for a variety of backbones. In general, self-supervised learning methods, even with a single global loss, are prone to collapse as the training objective admits trivial solutions. Using similarity matchings, the instabilities can be worse, as collapsed local representations lead to matchings where a single local representation is matched to all local representations in the other crop. When such dynamics are observed, the model cannot recover as the local loss makes it even worse. The geometric setting avoids this issue by construction. In conclusion, we leverage additional self-supervision by incorporating self-distillation at the local level and study the effect of the local matching function. A geometry-based matching function shows advantages over a similarity-based matching function, both in terms of higher performance on downstream tasks and better preservation of the spatial relations of the input image. This is particularly true in low data regimes, in which case we observe a collapse of the similarity-based matching function in some settings.